Welcome back to the deep dive. I was sitting in a coffee shop this morning trying to upload this massive video file, and the Wi-Fi was just thinking, that pause.
The spinning wheel of death.
Exactly, the spinning wheel. And it got me thinking about what is actually happening in that silence. We take it for granted, you click send, and we just expect this invisible traffic cop somewhere in the walls to make a split-second decision for millions of little envelopes of information.
It really is the invisible infrastructure of our lives.
Yeah.
We just expect it to work. But when you peel back the layers, which is what we're doing today with this stack of documents on router decision logic, you realize it's not magic.
No.
It's a very specific, very rigid set of rules.
Rigid is the right word. We aren't just talking about plugging in a cable and hoping for the best. We are talking about the brain of the internet. We're going to crack open a router and look at the actual decision loop, how it learns where the world is, how it decides which path to take, and then how it physically moves the data without crashing the whole system.
And the stakes are high. I mean, if that logic fails, or even just hiccups for a microsecond, the internet basically grinds to a halt. The router is the unsung hero that keeps modern civilization running.
No pressure, right? So let's start with the anatomy. The materials we have, they break the router's job down into two primary directives. They call them the control plane and the data plane. Now, to me, these sound like sci-fi terms.
They do a bit, but it's actually a really beautiful separation of duties. To understand it, you have to stop thinking about computers for a second. Think about a road trip.
Okay, I'm in the car. Snacks are packed.
Right. Before you even start the engine, what do? You sit down with the map, you look at the traffic reports, you look at the highways, you figure out, okay, to get to California, I need to take Route 66, then switch to I-40.
Okay.
That process, the planning, the consulting of the map, the intellectual work of building the route, that is the control plane.
So the control plane is the brain. It's the strategist.
Exactly. It's where the routing table lives. It's complex, it's thoughtful, and crucially, it takes a little bit of time. You don't want to be doing that while you're driving 70 miles an hour.
And the data plane.
The data plane is when you put down the map, grab the steering wheel, and just drive. You aren't analyzing traffic patterns anymore. You are physically moving the car from point A to point B. In a router, this is called packet forwarding. It's just taking data from the entry door, the ingress, and shoving it out the exit door, the egress.
The notes emphasize that we want these two things to be as separate as possible. Why is that? Why not just have the brain do the driving?
Because thinking is heavy. Thinking is slow. If you had to stop your car at every single intersection, unfold the map, and recalculate your route to California from scratch, you'd never get there.
You'd be the most annoying driver on the road.
Exactly. You want the thinking done beforehand so the driving can be automatic. You want the acting, the data plane, to be instantaneous.
Okay, that makes sense. So let's look at the thinking part first, the control plane. A router sits there, and it has this massive list of destinations, the routing table. But the internet is huge. When a packet arrives with a destination address, how does the router actually pick the right path?
This brings us to what I think is the most fundamental rule in all of networking. If you take nothing else away from this deep dive, remember this concept, the longest match rule.
It sounds like a game show, and now for the longest match.
It does, doesn't it? But it's basically a logic game. Here's the scenario. A router might know 3 or 4 different ways to get to a general area. It looks at its table and sees multiple options that could technically work.
But it can only pick one.
It can only pick one, and the rule is precision wins.
Let's walk through the example in the notes because I think it clears this up. We have a packet heading to the IP address 172.16.10.1.
It's that number in your head.
Right.
172.16.10.
Okay.
Now the router looks at its map and sees 3 potential paths. Path A goes to 172.16.0.012.
Okay.
Path B goes to 172.16.0.016. And path C goes to 172.16.0.026.
Now hold on. For listeners who aren't staring at binary code all day, those slash numbers, the 12, 18, 26, that's the subnet mask, right? That determines how specific the route is.
Exactly. Think of it like a zoom lens on a camera. Or better yet, think of it like addressing an envelope. The 12 is very broad. It matches only the first 12 bits of the address.
Okay.
It's like saying, I know how to get to the Western Hemisphere.
Okay, that's useful, but pretty vague.
Right. Then you have the 18. That matches 18 bits.
Yeah.
That's zoomed in more. It's like saying, I know how to get to the United States better. And the 26.
That's way more specific.
That matches 26 bits. That is a macro lens. That's saying, I know how to get to 123 Main Street, Springfield.
So even though all three of those technically include the destination.
The router ignores the vague ones. It always chooses the most specific longest match. It chooses the 26
Because it's safer.
because it's more precise. If I have a specific instruction for your street, I'm going to use that over a general instruction for your continent. It prevents the packet from getting lost in a big generic bucket.
That makes perfect sense. Precision over generality. But here is where my brain starts to hurt a little. We are talking about gigabytes of data, millions of packets per second. If the router has to do this longest match, comparison, checking the binary math bit by bit for every single packet, doesn't that take forever?
It used to. Oh, it absolutely used to. And this is where the history of router evolution of speed gets really fascinating. The diagram here shows the timeline of how they solved this problem. It's basically a history of engineers trying to overcome the limitations of physics.
Yeah, let's look at the dark ages first. It starts with something called process switching, and there's a little icon of a guy doing long division.
That is exactly what it was like. In the early days, the router's main CPU, the actual brain, had to wake up for every single packet. Every single one. Packet 1 comes in, CPU interrupts what it's doing, wakes up, looks at the destination, does the math, finds the exit, rewrites the header. Packet 2 comes in, CPU wakes up, does it all over again.
That sounds exhausting. It's like if I asked you, what is 15 divided by 3? And you worked it out on paper, and then 1 second later I ask, what is 15 divided by 3? And you start writing it out on paper again.
Exactly. You aren't learning, you're just churning. It crushed the processors. The internet would be incredibly slow if we still did this. So the engineers came up with fast switching.
Which I assume is?
Faster, much faster. It introduced the concept of a cache. So the first packet gets the full long division treatment. The CPU works it out. But then it stores the answer.
Like a cheat sheet.
Right. It says, okay, the flow going to 172.1.0.0 goes out port 4. So when the second, third, and millionth packet for that same video stream come through, the router just says, oh, I've seen you before. You go that way. It bypasses the brain entirely.
That sounds like a perfect solution. Why didn't we stop there?
Because the internet is messy. Caches time out. And you still have that delay on the very first packet. Plus, if the route changes, the cache is wrong. So Cisco developed what is now the gold standard, CEF, or Cisco Express Forwarding.
The notes mention CEF creates something called a FIBE.
Yeah, the forwarding information base.
Yeah.
CEF changed the game and said, why wait for the traffic to arrive to figure out the answer?
Right.
With CEF, the router pre-calculates the entire topology. It takes everything in the routing table and compiles it into a hard-coded structure, the FIB, before a single packet hits the wire.
So the answers are written down before the test even starts.
Exactly. It separates the control plane from the data plane completely. The hardware that moves the packets, the data plane, doesn't need to bother the main CPU at all. It just looks at the FIB and shoots the packet out. This is called working at line rate.
And this is why I can stream 4K video while on a video call without my router exploding.
Exactly. It's the only reason broadband works. Behind the scenes, there is this massive pre-calculated architectural feed happening just to shave off microseconds.
It's wild to think about. We get annoyed when a page loads in 3 seconds, but we don't realize the engineering required to make it load in 3 seconds instead of 3 minutes. So we know how it decides longest match and how it acts, CEF. But let's sit back to the learning phase. How does the router build this map in the first place? It doesn't just wake up knowing where Google is.
No, it starts with a blank slate. The documentation outlines 3 main ways a router learns. The first one is the easiest, directly connected,
Plug and play.
ideally. You plug a cable into the interface, you give it an IP address, and if the lights go green, what we call up, the router automatically adds that network to its table. It knows it because it's physically touching it.
Okay, straightforward. But you can't plug everything into one router. The internet is a web.
Right. So that brings us to source number 2, static routes. This is where the humans get involved.
The manual override.
Essentially, an administrator logs in, types a specific command. To get to network X, go through router Y.
The notes list some pros and cons here. On the pro side, it says secure and resource light.
It's secure because you aren't listening to outside rumors from other routers. You are telling the router exactly what to do. And it's resource light because the CPU doesn't have to run any complex algorithms to figure it out. It just follows orders.
But the comms list, it looks pretty heavy, hard to maintain. No automatic adaptability.
That is the killer. Imagine you hard code a route. You tell the router, always go down Main Street. But then a backhoe cuts the fiber optic cable on Main Street.
The router doesn't know the cable is cut.
It has no idea. It just keeps blindly sending traffic into the black hole because a human told it to.
Yeah.
It doesn't self-heal.
So static routes are good for small, simple things. The notes mention stub networks, which are basically dead ends. But for the messy, changing internet, we need something smarter.
Enter source number 3, dynamic routing protocols. Things like OSPF, EIGRP, BGP.
This is the robots talking to the robots.
Precisely. The routers send messages to each other. Hey, I see these networks. Oh, really? Well, I see these networks. They share their maps. And the magic feature here is self-healing.
Ah.
If that backhoe cuts the cable, the dynamic protocol notices the silence. It says Main Street is down, runs the math, and automatically reroutes traffic to the side streets.
That is the magic. That's what keeps us online when infrastructure fails. But this introduces a new problem, doesn't it? We have all these different sources of information.
Right.
What if they disagree? What if OSPF, the dynamic protocol, says, to get to the server, go left? But a static route typed by a human says, to get to the server, go right. Who wins?
This is one of my favorite concepts in networking because it's basically a trustworthiness meter. It's called administrative distance, or AD.
Administrative distance. It sounds like a corporate HR policy. Please keep your administrative distance.
It does, but it simply determines who the router believes. It's a ranking system. The rule is counterintuitive, though. The lower the number, the higher the trust.
Like golf, you want a low score.
Exactly. So let's look at the rankings in the chart. At the very top, with an AD of 0, is connected.
Absolute trust.
If I am physically plugged into it, I trust my own sensors more than anything else. 80, nothing beats it.
Then at 81, we have static route.
High trust. This is the administrator. The router assumes that if a human took the time to type this in, they must know what they are doing.
Then we drop down quite a bit. EIGRP is 90, OSPF is 110, and RIP, which is a great name for a dying protocol, is 120.
RIP is older, less sophisticated, so the router trusts it less. But look at the gap. Static is 1. OSPF is 110.
That's a huge gap. So to answer my question, if OSPF says left and the static route says right?
The router goes right every single time because the static route at 1 beats OSPF at 110.
So the router essentially says, I see what the algorithm is telling me, but the human gave me a direct order.
The router trusts the human. Hold on to that thought because that philosophy is really interesting when we think about the future of networking.
I definitely want to come back to that. But quickly, what if the conflict isn't between a human and a machine? What if it's two machines? What if I have two different OSPF paths to the same place? The trust score, the AD, is the same. It's 110 for both.
Great question. If the administrative distance is a tie, the router moves to the next tiebreaker. Metrics.
Metrics. This is the cost of the trip.
Exactly. But different protocols measure cost differently, and this can lead to some funny behavior. Take RIP, the old protocol. It uses hop count.
Hops just means how many routers do I have to pass through, right?
Yes. Distance. If path A is 2 hops and path B is 5 hops, RIP picks path A. It doesn't care if path A is a slow, rusty dial-up connection and path B is a super fast fiber optic cable.
It just counts the stops.
Just the stops.
Which seems incredibly flawed for the modern world. I'd rather take the longer highway than the shorter dirt road.
It is flawed. That's why OSPF is the standard today. OSPF calculates bandwidth. It looks at the speed. So OSPF would pick the fiber optic path even if it has more stops because the total travel time is lower. Lowest metric wins.
And if the metrics are exactly the same, if it's two identical highways,
then the router says wide shoes. It uses equal cost load balancing. It sends half the traffic down the left path and half down the right path. It uses both lanes of the highway.
Smart. So let's recap the logic loop so far, because it's building a picture. We've learned the routes. We've resolved conflicts with trust AD. We've broken ties with metrics. We've made the decision using the longest match rule. Now we actually have to move the packet. We are back to the acting phase.
Back to the data plane.
There is a specific detail in the packet lifecycle diagram about addresses that I found really clarifying. It's the difference between the IP address and the MSC address. I think a lot of people use those terms interchangeably, like they're just the address.
They do, but they have totally different jobs. Think of the IP address as the person you are writing a letter to. John Doe in New York City. That is written on the letter inside the envelope.
Okay.
That destination IP remains constant. From the moment it leaves your laptop until it hits the Google server, the destination IP never changes.
Okay, IP is the soul of the packet. It's the ultimate goal.
Right. But the MC address,
Yeah.
the MT address is the delivery truck. When a router receives a packet, it has to physically move it to the next router.
Hmm.
It takes the letter, the IP packet, strips off the old envelope, the layer 2 frame, and puts the packet into a new envelope.
A new envelope, why?
Because the MC address is only relevant for the local link. The MC address is just, get this to the next router. Once it gets there, that MC address is useless. So the router addresses the new envelope to the MC address of the next router in line.
So the letter stays the same, but it gets reboxed at every single stop.
Every single hop. The source calls this encapsulation and de-encapsulation. The MAC address changes a dozen times across the internet. The IKEY address stays end-to-end.
That's a great visual. The trek changes, but the cargo stays the same.
Now, before we wrap up the technical side, there is one safety net mentioned in the logic flow, the gateway of last resort.
Ah, yes. The 0.0.0.0 route.
The, ask the ISP route? Exactly. If a packet comes in and the router looks at the table and says, I have no idea where this IP is, no matches, nothing. It doesn't just drop it immediately. It checks for a default route. It's the funnel that catches everything else and sends it upstream, usually to your service provider.
It's the ultimate pass the buck. So this is all fascinating theory, but for the people listening who might actually want to see this in action, we aren't looking at electrons. How does a human actually check this brain? The notes have a section called the operator's toolkit.
Right. If you are a network engineer, you are living in the command line interface. It's a black screen with white text, no mouse, just you and the keyboard. The notes list the greatest hits, show IP route.
That displays the map, the full routing table.
And it can be huge, thousands of lines. That's where you see the codes we talked about. C for connected, S for static, O for OSPF. Then you have show IP interface brief.
That's just a quick health check, right?
Yeah. Are the cables plugged in? Are the lights green? It's the first thing you type when things break.
And show running config.
That shows you the active setup of the box. Everything the admin has typed. But the real pro tip in the notes, and I use this every day, is the pipe character. The vertical baris.
Oh yeah, the filter.
Because these outputs are massive. You don't want to scroll through 10,000 lines of code to find one address. So you type show IP route section, OSPF, and boom, the router cuts out everything else and just shows you the OSPF info. It's how you find the needle in the haystack.
It makes you feel a bit like a detective. You're interrogating the router. What do you know? Who told you that? Why are you sending traffic that way?
That is exactly what troubleshooting is. You are tracing the logic of the machine to find where it diverges from your intent.
So let's zoom out and look at the whole picture. We've covered a massive amount of ground today. It starts with learning. The router builds the table through connected interfaces, static input from humans, or dynamic protocols like OSPF.
But remember, it filters those inputs based on trust administrative distance. The human wins.
Then it moves to deciding. A packet arrives. The router uses the longest match rule to find the most precise path. If there are ties, it checks metrics.
And finally, acting. It uses CEF to instantly look up the answer in the cheat sheet, the FIB, re-encapsulates the packet with a new MC address, and shoots it out the egress interface.
And the cycle learn, decide, act happens not just once, but millions of times per second for every frame of this podcast you're listening to right now.
It's humbling, really. It's a level of orchestrated complexity that is almost hard to comprehend.
It really is. But before we go, I want to circle back to that thought about trust. We talked about administrative distance. The router trusts a static route, 81, more than a dynamic protocol, 8110. It trusts the human more than the machine.
That has always been the golden rule. The admin knows the business intent, the machine just knows the topology.
But think about where we are heading. Networks are becoming so massive, cloud computing, IoT, millions of devices, that no human can keep the whole map in their head anymore. And with AI-driven networking starting to emerge.
I see where you're going with this.
Is there going to come a day where we have to flip the administrative distance? Where we actually trust the machine more than the human? Where the router says, I know you typed in this static route, Dave, but my AI analysis says that path has 50% packet loss, so I'm ignoring you.
That is a provocative thought. We are seeing intent-based networking, where the human sets the goal, but the machine chooses the method. If the machine has a global view and predicts a traffic jam that the human can't see, maybe the machine should override the human.
Yeah.
We might be approaching the moment where the static route loses its crown.
Where the manual override becomes the less reliable option. Something to think about the next time you see that spinning wheel of death. It might just be the router disagreeing with you. That is it for this deep dive into the brain of the internet. Thanks for decoding router logic with us.
Always a pleasure.
We'll see you in the next one. Stay curious.